Okay, so after this motivation pep talk for variational inference, we will now start with actual content and talk first about Bayesian inference and some basic nomenclature in this regard. So I really assume that you are familiar with joint probability distribution, marginal probability distributions, and conditional probability distributions from studying the material and from watching the videos. If you are not, it will not necessarily be easy to understand what we are doing now. However, I will also not go into details about these things because you have the material and you can watch it. Yeah. Good, because the main aspect or the fundamental idea of Bayesian inference is a specific interpretation of conditioning and marginalizing joint probability distributions, and that will be the main point of what we are discussing now. So if you understand what a joint distribution of two random variables is and what a conditional distribution is, then understanding Bayesian inference is no problem at all. If you don't understand this, then it may be a little bit difficult. And that's why I said please look into joint distributions. So what we will first talk about, so to structure that a little bit, we will talk first about Bayesian parameter estimation, because that's one important aspect for Bayesian estimation and later variational estimation or inference. And then talk about Bayesian model comparison. Where the term of evidence will come up, and then of course we will look at an example, namely the univariate Gaussian and inference for its expectation parameter in the Bayesian setting. So that's the plan, and this is in the script, this is, or in the PMFN book, that's section 13.4, Bayesian inference in the probabilistic inference chapter. So there's first maximum likelihood, then it's a little bit of Fisher scoring, and then it's Bayesian inference, and we're talking about this Bayesian inference aspect now. So, first, parameter estimation. Of course, the whole thing unfolds, just to briefly remind you of that, the whole thing unfolds let's put it here, on the background of my general idea about, well, not my general idea, mankind's general idea of science, namely that you can formulate quantitative models, that you estimate them. So that's this intro lecture that you can also view in the GLM stuff, and I guess you've already seen model evaluation. And let me finish this. That there's this thing, that there's science which takes data and somehow brings data together with quantitative models, and based on this bringing together data and quantitative models, the models are evaluated. So it's that's investigated whether the models are any good, and if they can be improved, and usually can be improved, better models are formulated. And this whole process, of course, is called science. And data comes from the outside world, so this is the world. And Bayesian inference, like frequentist inference or any kind of statistics, is of course happening at this junction here, so bringing together the model and the data. So this is science. This is where this whole thing happens in a kind of the very big picture. Now, for Bayesian inference, where Bayesian inference starts is that a probabilistic model is formulated at least over two quantities, namely, I think I use a big P here, data. I also should use a big theta, parameters. So what this py theta should mean, it shouldn't really mean, technically it doesn't really mean much. It says that a joint probability distribution is formulated over data, whatever data are. So that depends, of course, on the specific scenario. So what was the data in DCM for fMRI? Of so the data for DCM for fMRI, as we discussed, were the average MR signal time series of a number of regions of interests. And for the mass univariate GLM, what was the data there? Yeah, the time series of single voxels, so the MR signal time series of single voxels. If of course, data can be anything. So if you record the reaction times of participants over many trials, the data are these reaction times of many subjects for many participants. So this is how you should think about data right now. It can be anything. Yeah? It doesn't usually. You can. I mean, what you can do is think of it as lists of data points or whatever. The important thing is that here we use a random variable to describe data in general, and an observed data set is then always interpreted as a specific realization of this random variable data. So this is of course important if you have a probability distributions over random variables, that the data and the parameters are modeled as random variables. And this is already, if you look at this, this is very different from what we did last year on the GLM, because what are the parameters of the GLM? Yeah, what do they quantify?
The influence of every single predictor.
And is there another parameter in the GLM?
As many beta parameters as we have.
But another class of parameters or one parameter?
We have an error.
We have an error, and is there a parameter for this error? No? Yeah, sigma square. So the parameters of the GLM were the beta parameters and the variance parameter. These parameters, when you remember when we talked about the GLM, they they are not specified in terms of a joint distribution over parameters and data in the frequentist setting. Yeah, they had, and this is important that you understand this, they had a distribution if we sample again and again from the probability of the data. So we had something that we call PY, which was a multivariate normal distribution over data and it was parameterized by the expectation parameter x beta and the covariance matrix sigma square in. But in the formulation of the probabilistic model, the data had a distribution, but the parameters had not. The parameters only had these observed probability distributions if we sample many y. Now, in the Bayesian viewpoint, we model we model parameters as random variables. So we say from the very beginning we have some probability distribution over parameters, and this probability distribution over parameters in data here. So this is not what we're talking about currently. This probability distribution over data and parameters is often called generative model. I personally don't like the term generative model too much because Felix always says it, and I'm never quite sure what he means by it, and I'm not quite sure he knows what he means by it. But if he would be here right now, he would say, no, I completely don't. So. Also, da stimme ich dir sofort zu, aber. So, the term generative model is used by many people, and it's so. So my definition, let's say it like this. I don't know what other people mean by generative models. What I mean by a generative model is a probabilistic model over data and parameters. Yeah, and by probabilistic model, data and parameters, and by probabilistic model, I mean a probability distribution. That's all. I just call it a probabilistic model because everybody always talks about models, and if people would ask me, do you do computational modeling? And I would say, well, I specify probability distributions and do inference on them. They would be like, so this is why I call this probabilistic models. Yeah, it's like that. It's sad, but it's like that. And of course, it also makes sense to spell out that probability distributions, the way they are used in scientific inference, are models. Yeah, probabilities are not real. Probabilities don't exist. They are mathematical models. Good. So this joint distribution over data and parameters is called a generative model. What the data are, of course, that depends on the problem, right? So we just heard that in DCM for fMRI, we have the time series over a couple of regions, or from a couple of regions. In mass univariate GLM analysis, which one can of course also do in a Bayesian setting, as we will see later. The data are the mass univariate, are the single voxel time series that are observed during a given run or multiple runs of an experiment. What parameters are also depends on the model of interest. Yeah. So, for example, in the GLM, we just heard that there are beta parameters and there are variance parameters. In DCM for fMRI, what are exemplary parameters in DCM for fMRI? Just anything, not all of them, but an example for a parameter in DCM for fMRI. The A matrix, which quantifies what?
A matrix that quantifies the influence of like all the regions of interest on all the other regions of interest.
Mm-hmm. And what exactly? What do you mean by influence?
The neural activity.
Yeah, but so what does it link in terms of the quantities that we described there?
Like how in an instantaneous moment, the neural activity, for example, A1, 3, how the neural activity in the region of interest 3 influences the neural activity in region of interest one?
Yeah, but what do you mean influences the neural activity? What do you mean by that? Mathematically. Yeah, so that is the important thing. So it quantifies how the state in a given area affects or influences the rate of change in a different area, because the whole thing is specified in terms of differential equations. Yeah. So it's not just that you add these neural activities and then you get the neural activity of another region, but it's the rate of change. That's the important thing. Yeah, so that's one parameter, and there are many other parameters, and you, of course, from thinking about this, you realize that different models have different parameter sets. Yeah? So the DCM model has, in this sense, many more parameters as the GLM model, like in a very simplified manner. So again, data and parameters in this setting depend on the specific modeling scenario. Yeah. So the way we describe things here right now is very general. So any kind of data, any kind of parameters. Parameters in this setting that have a probability distribution or that are part of the joint distribution over the data and parameters are in the Bayesian setting referred to as parameters. Of course, the whole kind of distribution can also have parameters. I'm just saying this here, not because it's horribly important, but sometimes I might come back to it. So, of course, there might be other parameters involved that specify the joint distribution. I will call them hyperparameters because they don't have a probability distribution. We might encounter that at some points, and sometimes you see the word hyperparameter, and the question is what it means. From my perspective, hyperparameters are parameters that don't have a probability distribution in this setting. And then you can go on and asking about parameters, do they change over time? Are they then rather latent states and so on? So one can look in more detail about these things, but for the moment we focus on the aspect that data are modeled by a random variable y and parameters are modeled by a random variable big theta. The whole thing is called, you can call it a generative model or a probabilistic model over data and parameters, or simply a joint distribution. It's a joint distribution, so for every pair of values that the data and the parameters take on, you get a probability. Yeah, so you define explicitly all the probabilities for y being small y and big theta being small theta for all y in the and theta, so for all values that data and parameters can take on, as is done in the probability mass distribution, in the joint distribution probability mass function in this Foundations of Probability Theory lecture. Yeah, so look into that if you haven't, so that you understand what I mean by this. If you don't fully, and I will now not ask who actually looked into that. Now, if you looked into that and you know, and you have a feeling about what a joint distribution is, you also will have come across Bayes' theorem, which is a way to compute conditional probabilities by not essentially looking at the joint distribution. So what's the definition of the conditional probability? If you have a joint distribution here, y theta, and you are interested in the conditional probability of theta given y, how do you compute this from the oops. Computer froze. Continues then. Okay, so if we have this, it's a little bit slow, I'm a little bit thick, but we are there. If we have this, I'm looking like I'm 10 when I write. If we have this joint distribution over y and theta, and we want to compute the conditional probability of theta given y, how do we compute this from the joint distribution?
The joint distribution divided by the marginal probability of y, I think.
Yeah, exactly. So, very good. So, of course, you always have to think that we can substitute all forms of values for y and theta. So the probability for big Y being 10 and theta being 5 or something, and this just describes this in general terms. And this is the definition of the conditional probability of theta given y. Now, Bayes' theorem, by doing this, and also by by basically doing this, equates the two conditional, the two joint distributions. So these are the same. So you have basically p, y, and theta equals p theta given y times py, and py being, I can just write it, that's quick. We have p theta given y, py equals this joint distribution. So py given theta p theta, and then if we divide both sides by py, we get what is known as Bayes' theorem. P theta given y equals py theta p theta divided by py. Yeah, so that's Bayes' theorem. Which just is a way to compute conditional probabilities on joint distributions. Now, the important thing for Bayesian inference is a specific interpretation of the quantities that you find in Bayes' theorem when formulated like this. Of course, usually what you have in Bayesian parameter estimation, let's write that down, parameter estimation. What you usually have, based on this general setting that you quantify, you formulate a quantitative model and you observe some data, you have an observation of observed data. Yeah, so you have observed data. So your random variable that models data has assumed or assumes some value, and in a way, in this joint distribution that you call your generative model, you assume that, and this is what makes things data versus parameters, you assume that these random variables are observable, and the parameters are unobservable. So this is the big difference between, from a probabilistic viewpoint, between data and parameters in the Bayesian setting. Some of them you can observe, so you can see what kind of values they assume, and other random variables in your models, you assume that you cannot directly observe them, but only infer about them based on your observed data. Now, if you have observed data, what you are interested in Bayesian parameter estimation is the posterior distribution over your parameters given your observed data. So that's the posterior distribution. And the posterior distribution, that's kind of the core thing for Bayesian and later then also variational inference. That's the core thing. So you have a quantification of your uncertainty over the parameter values for your observed data. No? To get to your posterior distribution, you have to, of course, evaluate the right-hand side of Bayes' theorem. And what you find there are first the probability of your observed data given your parameters, and this is what is called the likelihood. So calling this term likelihood is it's just the term that is used for this conditional probability. Is of course called like that because it relates very closely to the likelihood function that you know from classical or maximum likelihood inference. The difference, of course, here is that the parameters here are also a random variable, and in a typical likelihood function, they are just parameters of the likelihood function. It is, and this is sometimes very confusingly communicated, likelihood is nothing but a probability. Yeah, so there are some forms of probabilities which are probabilities, and there are other forms of probabilities which are likelihoods. No, there's just a condition. There are just conditional probabilities, and the conditional probability of observed data given a parameter is called likelihood. Yeah, but don't think much that there are no other. So sometimes you see when people write about this that they think that is somehow different. It's not different. It's just a conditional probability. Yeah? And then there is p theta, of course, on the right-hand side of Bayes' theorem, which is the marginal distribution of the parameters. So it assigns to each parameter value a probability for p theta assuming some value, and this is called the prior distribution. You might notice that kind of from a temporal sequence, I started with a posterior distribution and now in the end up with a prior distribution because I discussed Bayes' theorem from the left-hand side, so from here to the right-hand side. Of course, these things, prior distribution and posterior distribution, there is a connotation of order in them. So before observing, so the idea is that before observing the data, this is your quantification of uncertainty over the parameter, and after observing the data, so posterior to observing the data, this is your quantification of uncertainty over the parameter. That makes sense. But what I want to stress and what helped me a lot when I finally got that insight is that when you specify, because you specify two things in probabilistic model formulation, when you specify the likelihood and the prior, so prior and likelihood, when you specify these two things, and you have to, otherwise you cannot do Bayesian inference, you specify the joint distribution. Yeah? If you do this for all data points, you specify the joint distribution of all data points and, of course, all possible values for the parameter, which I don't make necessarily explicit here. So by specifying the prior and the likelihood, you specify the joint distribution, and the posterior distribution is already encoded in the joint distribution, yeah, because if this is the posterior, this is your joint, the marginal of y, you can just compute from the joint distribution by summing over all possible values of the parameters of theta, and so you can, based on the joint distribution, compute this whole thing. So your posterior distribution is specified as soon as you specify your model, namely your prior and your likelihood. And then you just basically select, based on some observation you made, you select to look into certain aspects of your joint distribution. I think this might get, or it should get even clearer when we look into the Gaussian example, which we definitely won't do today, but then next time. Then you see that maybe even more concretely how the joint distribution, so how the prior and the likelihood specify the joint distribution. This is your model, and then you observe something, and then you can compute its conditional probability under your model, but it's not that somehow the posterior distribution arises out of nothing suddenly once you observe some data. So this temporal sequence, and this is the point here, this temporal sequence from prior to posterior, it's artificial. It's not really there, yeah? Because once you specify your model, you have already specified your posterior, because your model is your joint distribution. And we will see that. Now, one thing in Bayes' theorem that is of interest, specifically if you're only interested in certain aspects of the posterior distribution, for example, where its maximum is, which you would, in parameter space, which you would then call the maximum a posteriori estimate. So let me briefly give you this. So MAP is the maximum over parameters of your posterior distribution. So for example, just to make this quickly, if this is your posterior distribution and this is your parameter space, then the MAP estimate is here. Yeah? If you're only interested in the maximum, you're not necessarily interested in that everything is nicely scaled. So a kind of mnemonic for Bayes' theorem is that the posterior is likelihood times prior. And so basically one ignores the denominator here, and then one has just likelihood times prior. Of course, this doesn't result in a proper probability distribution for the posterior, but if you're only interested in where its maximum is, you don't necessarily need this. Hence, this is sometimes useful. Specifically if it's not that easy to compute the marginal probability of the data. So if you think back about these joint distributions that we looked at in the introduction to probability theory, you will also realize that the qualitative aspects of the posterior distributions are the same as the joint distribution, but to make it integrate to one or sum to one needs to divide by the marginal probability of the data. Yeah, but you sometimes see this as a mnemonic. And sometimes, if you're only interested in the MAP, for example, you're not interested in the value of the actual probability, but you're interested in the location of the maximum, and then this can help. There's another aspect that people like to sometimes quantify about posterior distributions, which are intervals in which parameters lie. These are then called credible intervals. Yeah? It's a little bit like a it's not at all like a confidence interval, but the general idea to say, okay, parameters, I don't want to talk about confidence intervals right now, but instead of just saying, okay, the probability for the parameter to assume the value x is that, specifically if you have parametric and probability density functions for the posterior distribution, you might want to say the probability for the parameter to be larger than 0, for example, is that and that. And then you specified a credible interval between 0 and infinity. Yeah. So this is just a term that I want to say and make sure you have heard. So credible intervals. Good. Finally, this was basically Bayesian parameter inference in very general terms. Where are we? Bayesian parameter inference or parameter estimation. So you create a posterior distribution over parameters based on your joint distribution. The other thing is that what you want to do is Bayesian model comparison. Yeah? So one thing is to make statements about the parameters. The other thing is to make statements about the model as a whole. Bayesian model comparison. And for this, if you want to compare different models, of course, you need first to have different models. Yeah? If you only have one model, there's not much you can do with model comparison. But if you have two models, meaning two joint distributions over data and parameters, which are now called P1 and P2, so we have two generative models or two probabilistic models or two joint distributions over data and parameters, and we assume that the data random variable is not the same, but it can take on the same values in both cases. Yeah. So of course it doesn't make sense if to compare different models for different kinds of data. Well, one can think about it and create maybe something that allows for that. But in general, we are interested in explaining the same kind of data. So either single voxel time series or regions of interest or voxel time series with different probability distributions. Yeah. Same data, different models. That's the usual case, meaning that the data variable in these models needs to be somehow similar. What we then can look at is the probability of the data Py under model 1 and compare this to the probability of the data under model 2. And this is nothing but the marginal probability of data y under P1. So under our first joint distribution, and this is of course the same thing under P2. And the question is, which is higher? So under which model does the observed data have a higher probability? And this is the standard criterion for comparing different models in the Bayesian setting, and if this marginal probability is higher for model P1, then one says there's more evidence for model 1. This is why again coming back to Bayes' theorem, in Bayes' theorem, as you remember from just a second ago, in the denominator we have Py. And Py you can, of course, because it's just the marginal probability of the data, where I'm here just writing that I'm integrating out the parameters. Of course, you can, if the parameters are discrete, you can also sum them out, like we did in the probabilistic foundation scenario. this thing, because this marginal probability can serve as a model comparison criterion, is called the model evidence. Yeah? Question?
Okay, why do we use the marginal probability, not the conditional one? Because actually what is important for the model isn't it like the parameters? When we compare two models, isn't it like we're comparing them based on the parameters? Yeah,
but which conditional one do you mean?
So that should be the, wait, I have to look at it. It should be the likelihood actually. So
yeah, but the likelihood is something that you define. So the likelihood, so you have to specify the likelihood based on what you think, given a given parameter combination, the probability of some data is.
Okay, but what about if you use the posterior? So so under why don't you use just the posterior? So just comparing the different posterior distributions actually, which is higher.
But the posterior distribution is a probability distribution over the parameters, and you want to say something about the probability of the data under your model. So you have two posterior distributions, and you can say something about the parameters. So this parameter has a higher probability than this.
So which parameters fit better to the data?
Yeah, but this of course depends on your overall model, and you want to compare the models and not the parameter distributions. Actually, I see your intuition, and in some way I agree with your intuition that so what you have in mind a little bit is the idea of likelihood comparison. So that you what you do if you do likelihood comparison, what you do is you use your maximum likelihood estimate. So you have some parameter which you have optimized. So you have a maximum likelihood estimate, and then you compare this, and this you can call model 1. Let's put a little 1 there, and you compare this to the optimized optimized probability, so to the probability of the data under the best parameter estimate, and you have something in mind like that. The thing is, the idea here of this kind of setting is that you basically ask the question of how flexible the model is, and you penalize more complex models in the sense that if you have a model that because of its prior distribution, because of this, can explain a lot of data, then you say it's not that special if it can explain a lot of data. So if the prior is very flat, but if the prior is fairly specific, so it says these kind of parameters have a high probability, and it explains the data, then you don't penalize that as much, and you basically say that's then a very good model. So that's kind of the model evidence idea that is behind that. The question is whether I want to explain this more or I don't want to explain this more. So the important thing is one can explain this more, so one can draw little things about and give this intuition. The thing is, it will not change, and it will remain that this is the model comparison criterion that is used in Bayesian inference and also variational inference. Let me have a think. I really have a lot to do this week and next week, so I'm not quite sure that I can prepare something along these lines in the meantime. The thing is, it makes, so the thing is, first of all, this is how it is, and we can say we like it or we don't. This is how it is. If we don't like it, we can do something else. What you have proposed so far doesn't quite work, so we haven't quite found a constructive alternative. although there may be some. And we haven't really delved deep into the interpretation of the model evidence. So I just explained verbally that this penalizes flexible models and favors non-flexible models, because non-flexible models are, of course, more specific, right? So if you have a model where you say, okay, things are like this and this, and explains the data, then this is a very good model. If you say, well, my model can do everything and explain this data, that's not a very nice model. So flat priors are generally need to be disfavored, and also what needs to be disfavored is large deviations from the prior in terms of the posterior. This is the whole model evidence intuition. Yeah, maybe I can create something along these lines. The thing is, this is just the intuition on which the whole rest of variation inference is based. And if we talk long about this, then we might not get far with other stuff.
So just a quick question. Basically, the difference between using these marginal probabilities and what Alex and actually also I were thinking, would be that in that case we focus on the whole model, meaning not only like the maximum of the distribution, which would be only the parameter, but also like on the variance, like how our distribution is shaped, right? Because we take into account like how specific the model would be.
Yeah, and you can say like this. Yeah. So you should not even start to try to think too much about this when you talk about Bayesian inference, because what you were trying to do was something like this, like taking into account the variance versus just taking But this does not happen in Bayesian inference, so that doesn't exist. So don't go down this route and mixing these two things up. In Bayesian inference, you have probability distributions over parameters, and you will always have probability distributions over parameters. And then it doesn't make sense to think about what would happen if I only had a given parameter value. That doesn't exist. So
yeah, that's what I was referring to. Like by using the marginal probabilities, we don't do that. Right?
We don't do that. Yeah, exactly. But we also cannot do that in the Bayesian setting because we always have probability distributions over. So as this comes up, and this also confuses colleague Blankenburg all the time, and this is why I look a little bit, because I always get these questions, and I know where this is all written down, the things that I haven't written it up, and if I haven't written it up, spelled it out explicitly, then everybody's still confused. And this always leaves me a little bit like, why do I have to do everything? But I think what I can do definitely is, or what I should, although I have to actually submit applications for a new job this week. What I might be able to do is to extend this example of the Gaussian and using two generative models, one of which is more flexible and one of which is less flexible, so that you see again this intuition. Yeah, I put this down because now this is in the room, and you will not be satisfied until this is answered, because not even this basic question was answered, and then we had to talk about variational calculus, and this is what I've now put down in my evaluation. So okay, yeah, I will try to do that, but keep this whole thing in. Yeah, try to the most important thing about this whole thing is that we're talking about joint probability distributions and their interpretation in terms of scientific modeling. This is the main thing. Yeah? And if you read different things elsewhere, that you start with some idea about what your parameters might be, and then you do a prior, and then somewhere the likelihood appears, which might be something different from a probability. Yeah, you specify a joint distribution over parameters and data, and then you look at the conditional of the parameters given some data, and you look at the marginal probability of some observed data under your model and compare that to the marginal probability of your data under a different model, and then you compare the two. That's what Bayesian inference rests on, whether you like it or not. And also variational inference, which then, and we will get to that maybe to give you a first idea about this. Variational inference kicks in if doing this is not that easy. If computing conditional probabilities is not easy, then variational inference starts to essentially approximate this, and to also approximate this. And how is the approximation called for the evidence in cognitive neuroscience? I haven't told you. It's called, in the real world, it's called elbow, because it's the evidence lower bound. We will get to that. In cognitive neuroscience, it's the free energy. But we will get to that. This is just a teaser. That doesn't make any sense right now. It also later doesn't make sense why it's necessarily called free energy, but it's just a teaser. Okay, then let's stop here if there are no further questions right now, or are there? Yeah.
Just very small one. The data likelihood is always the P, and then Y comes first, and then the parameters. So it's over Y because it's differently in the text and script right above the formula 9.36.
9?
9.36.
13.36.
9.36 is page 105.
Yeah, I see that there is a mistake, but I have a number where it's 13. Yeah, so it's y given theta. That's the likelihood, and this is a typo.
Okay.
Yep. Good. Then let's have a break and start then later with programming.